Welcome to another edition of Samsung's Tech Talk. I'm Sarah Peach, Senior Director of Memory Marketing for Samsung Semiconductor. Our topic for this episode is the trends that are driving the future of high-performance computing, or HPC. And I'm so pleased to introduce my two guests, both of whom are renowned experts in the area of high-performance computing, and both are leaders in the Samsung Advanced Institute of Technology, also known as SATE. Robert Wisniewski, or Bob, is Senior Vice President and Chief Architect of HPC and Head of SATE's Systems Architecture Lab. And Samantha Kasuri, Vice President and Chief Hardware Architect of HPC in the Systems Architecture Lab. So hello and welcome to you both.
Well, thank you, Sarah. It's great to be here.
Yeah, hello. Thank you for inviting us for this.
Perhaps the best place to start is with a definition of high-performance computing. So Bob, how does the Systems Architecture Lab at SATE characterize HPC?
Yeah, no, thanks, Sarah. That's a great question to start with because in some sense, HPC has really been changing over time, right? In the last 5 years, especially with the advent of AI, it's morphed quite a bit. So a great place to start. So high performance computing, oftentimes, as you indicate, we say HPC, encompasses bringing together many different, what we would normally think of as individual machines, be them CPUs, GPUs, or other types of technology. And I'll say something very briefly about that. But most importantly is bringing lots of compute capability in a highly synchronized manner to solve a problem. And that's important because when you think about cloud, cloud and HPC oftentimes are both viewed as very large, right? And one of the distinguishing characteristics about HPC is not just the scale, but the very tightly synchronized manner characterized by low latencies between the machines, as well as high network performance. So in the end, HPC now has changed in some sense. Traditionally, HPC applications have been modeling and simulation applications, and I'll just give a few examples of those. Scientists oftentimes study the collision of galaxies. That's a modeling and simulation application, figure out how they would come together. More down to earth, simulating the airflow over a plane's wing or over a car body, something that has tremendously actually saved car companies billions of dollars and reduced the cycle times in terms of designing new cars. So those are big problems, but even traditional HPC has smaller problems. I grew up as a swimmer, and one of my favorite examples is to talk about applying HPC to the design of swimsuits and the fact that once they started modeling them, they actually realized that if you take a look at shark skins, it had small aberrations rather than very sheer swimsuits, which is what we used when I was growing up. So they actually, Speedo came out with this new suit called a shark skin suit. So it affects our everyday lives too. But more interestingly, and pertinent to the question that you asked, is the fact that HPC has changed because nowadays AI, machine learning, and deep learning techniques are just as much a part of HPC as the traditional modeling and simulation applications that we previously thought of. And there's twofold. One of them is just doing AI for the AI and machine learning, deep learning aspect of it. A lot of very interesting problems that you've seen in the news are contained in that space. But the other very interesting angle is a lot of traditional modeling and simulation applications are encompassing taking AI techniques and including them in the applications themselves. So HPC today, everybody now is doing HPC in some sense. It's just about getting really good performance across a whole varied set of applications in a tightly synchronized and very high performance manner. Thank you.
Okay. All right. Well, that's a great definition. Where you've described that AI is really the focus today, what's HPC going to look like in, say, 5, 10, or 20 years' time?
Yeah, well, let me give a quick start to that, and I'll have my good colleague Samantha follow up and provide some more detail. So the first thing is, over time, HPC has changed, and just like we're familiar that computing has changed, right? Your phone today is like your old massive PC of yesterday, right? And HPC is going through similar transitions. Today, HPC is viewed as massively parallel. That was a transition we made 2 decades ago. Today, HPC is also a term we call heterogeneous. It's not just about CPUs, but it's about using CPUs and accelerators. One of the things that we'll talk about throughout this conversation that I'll introduce now is there's two big challenges that we're seeing in HPC to allow applications to continue to drive forward. One of them is memory bandwidth. Data, of course, is becoming increasingly important, especially with the advent of AI. And being able to access large amounts of data very quickly is just so key to being able to drive HPC forward. And very closely related to that is the communication bandwidth. So where we view that HPC is going now is something that we're calling memory coupled compute. And I'll let Semantica just talk about a little bit more of that vision.
Thanks, Bob. That's a great start. So HPC really, as Bob said, is very pervasive. And we have found that HPC oftentimes is the leading edge, in terms of technologies that get adopted across the industry. HPC is the start, it really drives forward based on requirements because of the scale that HPC has. And then, data centers, cloud service providers, even all the way down to consumer electronics tend to pick up technologies from HPC, which is why it's so important that Samsung is developing this memory coupled compute, as Bob pointed out, because this is HPC and it will really help HPC, but it has a pervasive impact across the computing industry. That's what we believe. So what is memory coupled compute? So we oftentimes think of memory and compute as two distinct entities. And traditionally, compute has been the driver. Think about CPUs, think about accelerators, that's where the smarts are. That's where we really believe the power, if you will, is. And memory is thought of as an auxiliary structure or more of a support function, right? What is memory? It's something that holds some data that the compute part wants to operate on. What we are trying to do here is break that dichotomy and sort of bring them closer together. We're saying memory coupled compute means that memory is now going to be an active participant in the entire computing paradigm. And by bringing memory and compute closer together and coupling that with communication, we will break that memory and communication wall because you now have all three pillars working together. So that's the general vision of memory coupled compute. And there are instantiations that have gone in this direction. So when we started first with memory and compute, they're very distinct, connected with cables that were quite long. More recently, we've been focusing on packaging strategies that bring memory closer to compute. Think 2.5 dimensional strategies. So you have memory, you have compute, but you have shorter pins and shorter distances for them to travel. That improves the problem, but it doesn't completely avoid it. What we are talking about is taking that further and pretty much bringing the distance between memory and compute as close as possible. So what does that give you? It gives you lower latency to access data that's in the memory. This will help the compute go faster. It will help the compute run at lower power. Not only that, it also breaks this trade-off constraint that vendors have to deal with, which is cost. When you think of an entire system cost, and I can't emphasize enough how much from a systems perspective this lab, systems architecture lab, is going to look at things. That's what led us to memory coupled compute. When you look at a system perspective, the cost factor always tends to move the trade-off in one direction or the other. If you have to pay more for compute, you pay less for memory and you pay less for the communication. It's, you have to take from one to pay the other. It's just the cost function. What we are trying to do is break that cost constraint and say by coupling the three together, you don't have to choose between one or the other. So as I mentioned, when we did the 2.5 dimensional packaging, you got memory closer to compute. What Samsung's vision for memory coupled compute is we will further bring memory and compute closer together, couple them together so that those distances, those latencies, the power, the cost, all those factors tend to come down even more.
Yeah, that's great. I'd like to get your insight into the business and the technology trends that are driving the need for memory coupled compute. You hinted at a few, perhaps you could describe in more detail. Maybe Bob, start.
Yeah,
on this?
that would be great, and I think Semantic had a wonderful start on that. So there's a couple trends. I'm sure some people are, everybody's familiar, I should say, with cloud, right? HPC is becoming a lot more ubiquitous than it was 10, 15 years ago, and there's two trends that are driving that, and it really does have profound impacts on the business model and how vendors as well as consumers utilize HPC. So the first is that just the computing power in general has increased. And what this means is that, the bar to actually being able to do the types of problems that we talked about, as well as other interesting problems, is some sense much more achievable by a much larger audience. And so HPC really truly can affect our everyday lives now versus 20 years ago, where it was a tool for scientists. And because of that, clouds are now starting to provide some basic HPC services. So with that as a backdrop, it's important for vendors, Samsung playing in the memory space, Nvidia playing in the GPU space, Intel, AMD playing in the CPU space, all of those vendors, focusing on HPC. It's important to look at it from a different model, and that is, it's not just a very high touch point-to-point communication or arrangement with a particular organization, right? HPC now really, as I mentioned, is either broad among a set of end customers or broad among CSPs. So it's important as we think about our technologies, and as we think about, more importantly, designing the software stack, we make it a lot more accessible, a lot more productive. And there's different activities that lead us in that direction. One of them that I was previously and will continue to be involved with is something called OpenHPC. It makes we call it the democratization of HPC, but it allows HPC to get out into the hands of end users, of people much more broadly. So, in some sense, what we really need to do then is we need to have this, through either CSPs or through this more ubiquitous sort of, channel and ecosystem. We need to be able to think about HPC from a much broader sense than what we used to do. And so that has both the business implications as well as, technology implications, as we're designing the components, as we're designing the software that's going to run on the components, and as we're partnering with applications, which in the end is why we design the hardware, why we design the software for these machines. We have to have that model in mind. So it's a combination, like you indicated, Sarah, of both the business and the technological aspects coming together.
Mm-hmm. Great. Well, the next question I'd like to ask is for Semantica, and it's focusing on the systems architecture lab at SAIT. And from the name of the lab, right, the focus is at the systems level. So I'd like to ask what kinds of advancements you are hoping to potentially unlock at that level.
Sure, thanks, Sarah. So yes, the lab is titled the Systems Architecture Lab for good reason. There are a lot of research labs in industry, and they do really good work. And a lot of labs really look at key components and key aspects of the system and, really drive technology advancements in there. And what I have found over several years that I've spent working in computing and HPC is that the trade-offs and the decision-making process that goes into looking at things from a systems perspective sometimes is very different from looking at things at a component level perspective. Let me give you one simple example. When you think about efficiency, right, and you think about a small component, you might tell yourself, well, let me take that small component, right, and run it as fast as possible, right? I'll get the most efficient, performance from it, like a car, right? But if you had a fleet of cars going together, right, a huge fleet of cars going together, and if one of those cars goes really fast, but a car right behind is lagging, what does that happen, right? The first car will be forced to slow down at some point, and eventually you may not make a lot of headway or progress in getting from point A to point B because you looked at a single car in isolation without looking at all the cars in the fleet. Looking at systems is very similar, right? when I look at just one component or just one CPU or just one accelerator, I might make a decision to run that as fast as possible at its highest possible frequency and tell myself I'm getting the highest performance. But that may not matter at a systems perspective if another component is going slower, if, say, the memory is going slower, or if the network communication is going slower, or if for some reason one of the other CPUs is lagging behind. So when you look at things from a systems perspective, we find that the trade-offs we make may tell you, well, run all the components a little bit slower than their maximum speed, but make sure they all run in the same range of speeds. This is just one example of one possible trade-off. And you'll find that by doing that sort of, trade-off at a systems perspective, you oftentimes tend to reach a more optimal point than looking at things from just a single perspective. So I think what we want to put forward is the driving vision of our lab is to look at things from a systems perspective and really try to build very simple, reliable building blocks and scale them out into a large system and then have them all operate similar to each other, not have one go very fast or one go very slow, and just sort of reach an optimal point at a systems perspective. The second quick example that I might try to point out is that at a systems perspective, data movement looks a lot different than just at a component perspective. At a component perspective, right, you might just look at it and say, let me add what we call classically a cache. Okay, a cache is a small component where you speed up sort of memory latency by adding it. At a systems perspective, adding a layer of cache may not be the right answer by itself. What you might instead want to do is reduce the latency to access memory of a remote node or a remote compute. So in my car example, right, you might say, oh, let me just take this one car, add this one feature in there, and that car will do much better. But maybe what you really want to do is add a stronger cable between the cars so they stay close to each other and they're able to sort of, drive off each other. So these are just a few sort of real world examples, I think, that I could apply that when you look at things from a systems perspective, you can reach a more optimal point.
Yeah.
No, that makes a lot of sense. What about the software aspects when you're looking at a system level?
Yeah, no, thanks for including that, Sarah. So Semantica talked about the systems lab as looking at things from an overall perspective. And I think she did a great job of describing all the different aspects when you're looking at the hardware. But in the end, the system contains all of the hardware, all of the coordination, synchronization, and then it includes a software stack and the application. So in addition to doing all the wonderful things that Semantica has described, in the systems architecture lab, we are also involving software. And we do a co-design, and this is an overused term, it really is. But what it really means is that our hardware teams, our system software teams, and our application teams are going to sit down together and make sure the overall system is the most productive it can be. There's many times where there's great, wonderful ideas in hardware that on paper, if you just do the analysis, will have really good performance. But then when you go to utilize them and expose them through the system software, it's very hard. And you aren't able to get all of that potentially promised performance that came out of the hardware. And so by having all three of these teams doing the systems design together, in the end, what we wind up with a system that best leverages all that really great hardware that Semantica talked about, and also is able to expose that up to the applications, which in the end are what needs to run. And so part of it is understanding what the system software needs to do to be able to expose the hardware. But part of it is also understanding the needs of the applications and what they, what flexibility, what range of options they have in terms of when they're programming things and what they need, not just from the hardware exposed to the system software, but what we can also do from a system software point of view too. So not only will we have a lot of innovations in the systems architecture lab on the hardware, we will also have innovations on the system software as well, and we'll of course be partnering very closely with the applications who are then putting together the entire picture of bringing that hardware, exposing it in an effective way through the system software, and leveraging it to drive new science and engineering. Thanks.
Great. Well, now Now you've given such a great rationale for a system level view. I'm going to pull you right down to the component level because I understand your research is at the system level, but I'm coming from the memory business at Samsung. So I'm really curious to learn how memory and storage technology specifically need to evolve to move HPC forwards.
Sure.
Maybe Samantha
Yeah,
can
I can
start with this.
start, and Bob, please augment it, as you see fit. So, yeah, so, memory has come a long way since when I was a grad student and I was looking at memory technologies, right? Back then, high bandwidth memory didn't exist. This notion of HBM, which Samsung is a pioneer in, really, and has transformed the world of computing, at least for us in HPC, didn't exist. And so, we started with DRAM. We kept trying to make those faster, through frequencies, through various advancements, through latencies, etc. And, we found that while doing that really helped applications, more and more applications were so severely memory bandwidth limited that even small increases in memory bandwidth led to dramatic increases in performance. And so, experts like the ones in Samsung's packaging space and other, memory vendors started looking at, okay, what kind of packaging techniques can I take with DRAM dies and make them, faster, make them more efficient, reduce the power, reduce the cost, and how can I put it together in a form factor that really enables them to be used in HPC systems, data centers, etc. And, that's how basically HBM was born. And as I mentioned, that's pretty much transformed the current state of HPC, and all our current exascale machines, we're in the exascale era, really rely on HBM as almost a fundamental component to give that performance. So, looking further, what's ahead? Do we stop at just that? I don't think so. And, again, Samsung being sort of the world leader in this space has started actually building processing in memory, not just as an abstract concept or a research paper where it's been for a long time, but as a real technology that can be used. So Samsung's PIM technology that's used both in HBM and in other memory technologies basically does, augments memory with small amounts of compute. And I say small because, when you augment memory with compute, you want to make sure you don't take away memory capacity. You don't want to take away the fundamental principles and value of memory by flooding it with compute. So when you think of something like the PIM technologies, they really are augmenting memory with very simple, small type of operations that can be done with memory. And I believe that's a great way forward, because there are a lot of operations that can be done at that level. So, I think PIM is something that we'll see more of. We'll see Samsung taking that forward in different ways. We'll see other companies as well sort of, jumping on that bandwagon, seeing the value and continuing. And then, of course, our memory coupled compute, vision that we spoke about. And, I don't know if Bob's mentioned this or not, but we really see this not just as a niche HPC space, right? We think memory coupled compute eventually will be wherever, in all places that we see HBM in, where we see the value of memory bandwidth, memory latency. So, I think that's sort of the way forward if you think about memory roadmaps. You also mentioned storage, so I'll very quickly talk about that, and I'll hand it over to Bob. Now, there's been a lot of advancements in storage. So, we have non-volatile memory, again, sort of almost like an invisible backbone of large systems, because while memory is where active data sets and active working sets reside, storage is where, the backbone, the much larger amount of data lives. And so I think storage is also going to make a lot of advancements in terms of technology, and the faster it gets. So now we're sort of in this phase where we think of storage, whether it is, when we started, it was with hard disk drives. Now we have fast solid state drives. So it's getting faster and faster, and, leading to like storage tiers, like hot storage, cold storage, and really optimizing that. But again, I think fundamentally what we are doing in SAL by focusing on data movement, by focusing on reducing communication costs, is going to help storage. Because if you can get to storage faster, right, at lower cost, with lower power and lower energy, then you can do things like checkpointing more often. You can store checkpoints faster. So I think what we're doing at SAL is going to drive sort of the technology roadmap of both memory and storage much further.
Well, this has been a fascinating discussion, and it's clearly an exciting time to be working in the area. So, Bob, are there any final thoughts you'd like to leave us with regarding the future of HPC?
Yeah, that'd be great. So let me just take us back to the beginning, actually, to talk about how we're going to go to the future. So if you take a look at 40, 50 years ago, HPC, in fact, just computing in general, was take a single core and run it as fast as you could. And then, of course, we all have heard about Moore's Law and how technology companies have been able to increase exponentially over time. The interesting thing is when you take a look at HPC, and again, Symantec and I have talked throughout this discussion how HPC and AI are representative of the broader market. It turns out that the advances that we've made in terms of performance and realized application capability have exponentially exceeded Moore's Law. And you ask, well, how did we do that? And it's through a series of what I call discontinuities. The first big one, many, many years ago, was vector computing, the ability to pull in and do operations on multiple different pieces of data, sort of with the same instruction. And the crazy supercomputing realm was born. In the mid 90s, there was something that we're all very familiar with that we have all, in our phones and our desktops called microprocessors. And they moved HPC and computing to this era of distributed computing, again, giving us yet another exponential increase over what a typical Moore's Law would have done. Going forward in the early 2000s, it wasn't just about a core anymore. There were multiple cores on a chip and multiple threads within a core. Again, getting us another factor. In the mid 2000s, I had an opportunity to participate in a supercomputing effort called Blue Gene, which showed how to go from roughly 1,000 nodes to 100,000 nodes. Again, giving us yet these additional orders of magnitude. And today, as we've already talked about, we're in the discontinuity era of heterogeneity. We're using accelerators, we're using GPUs, which give us, as people know, this additional factor, especially in AI, but even in compute, over what a CPU was. The vision going forward that we've shared with you and that we're all very excited about, and Samsung is the right and well-positioned company to do this, is what we're calling memory-coupled compute. Just like today, if you take a look at your watch, your phone, your computer, they're all using a lot of these technologies, multi-cores, vectors. Our vision is 20 years from now, all computing is going to be memory-coupled compute, bringing that ever important part of computing, memory, and the actual computing closer together to get greater efficiencies at a lower power, at a better cost performance. So we're just very excited with the work that we're doing here at Samsung in the Systems Architecture Lab to be pioneering, to be figuring out how to take this, critical piece of the system, memory, and bring it together with compute and look at it from an overall systems perspective. So just, thank you, Sarah. Thank you to the team for coming together. We're delighted to be able to share this, and we hope everybody is excited as we are about where technology is going.
Well, I can feel that excitement. For sure, it's a good time to be in HPC. So Symantec and Bob, thank you very much for sharing your deep knowledge and insight into what it's going to take to move HPC forwards.
Thank you.
Thank you.
And it's great to learn. Oh, sure. Great to learn about these applications, not just about how to make you swim faster, but applications that are critical to business and also important to society as a whole. So I very much hope we can pick up this conversation again in the near future, as there's clearly a lot more to understand about HPC and how it's going to be a game changer for us.
Great. Thank you.
So thank you. And until next time, I'm Sarah Peach from Samsung Semiconductor.